for Maths A2 Unit 3, the chain rule. The chain rule deals with composite functions, and a composite function is a function of a function. So we can think of it like this. We have a value, x, we put it through a function g, and that gives us an answer g of x. We can then put that value through another function f, and then the outcome is then f of g of x. So in this situation, the function g acts on x, and then the answer is acted on by f. And it makes much more sense when you have a look at an actual example. So if we have g of x is x squared plus 2x minus 3, and f of x is x cubed, what is f of g of 3? Well, first of all, we have to allow g to act on 3, so that means putting 3 into the equation for g, or the formula for g, which gives us our 3 squared plus 2 times 3 take away 3, and so on, and we end up getting 12. Then we put the answer, the g of 3, which is 12, into the function f. F is x cubed, so that means it's going to be 12 cubed, which gives us 1728. Using the previous notation, what we have now is that x is going via g to g of x, and then g of x goes via f to f of g of x. So 3 went in, g of 3 came out, that then went into f, so we had f of g of 3. So 3, when it went through g, gave us 12, and then when that 12 went through f, we got our 1728. So, what is the chain rule? So, we're going to look at the motivation, so why we want a chain rule, or function of a function rule. Now, we know how to differentiate our x squared plus 2x minus 3, and we know how to differentiate x cubed. What if we had to differentiate the composite function x squared plus 2x minus 3 all cubed? So this is using the example we've looked at with numbers, but now looking at it as functions. So we're putting our function g and making f, which is the x cubed, act upon it. As I've mentioned, the chain rule is also called the function of a function rule, and it's important to think of it that way because then you can think of the function acting on a function which acts on a number, and later you'll look at the product rule, which is a slightly different situation. It's important to know the difference. Okay, so what we could do with this is we could multiply it out. So that means having those three things, the x squared, the 2x minus 3, and cubing it. Now, obviously that's going to take a while, and it will be very easy to make a slip or two, but it comes out as this. So y equals x to the power 6 plus 6x to the 5 plus 3x to the 4 minus 28x cubed minus 9x squared plus 54x minus 27. And I did all of that without taking a breath, but it was difficult, and that is a nasty looking thing, and it took a long time to multiply them out. So if there's a better way of doing it, we should perhaps find it. Now, the other thing is, of course, even when you've done all that, you've then got to differentiate each of the bits, which is going to take another bit of a while. So, is there a shortcut? So, we're going to build up to how this works by looking at some slightly easier examples. So if we start with y is x plus 1 squared, then we can multiply that out nice and easy, x squared plus 2x plus 1, and then we can differentiate. So that gives us 2x plus 2. Slightly more difficult, but not much, is y equals 5x plus 2 squared. Multiply that out and we get our 25x squared. 2 times 5x times 2, which gives us 20x, and then the 2 squared gives us 4, and then we differentiate that separately, and that gives us 50x plus 20, and we can factorise that to give us 10 times 5x plus 2. What about this now? This is another sort of little step up, because instead of an x in the bracket we have an x squared, but it's still basically fairly easy. So we have 3x squared. When we square that, we get 9x to the power 4. We then have our 2 times 3x squared plus times 7, which gives us 42x squared, and then we have our 7 squared. We differentiate that and get 36x cubed, which is 4 times 9 times x cubed, and then we get 84x. Factorise that, and we can take an x out this time, so we get 12x times 3x squared plus 7. So there's some examples, and we can put them into a table like this, and we can see that we've got each of those functions in the y column and then their derivatives in the dy by dx column. Now, what do we notice? Do we notice anything? Well, you might notice something, but there's a nice way of helping you to notice something, which is to add another column. And we can see that each of those numbers in the middle column now is even, which means we can take a factor of 2 out. So each of them has got a 2. We can then see that we've got a 5 with the 5x plus 2 bracket, and we've got 6x with the 3x squared plus 7 bracket. Now some of you might notice there's something interesting happening there, but we are going to look at that last example and pick it apart, as it were. So we've got the function 3x squared plus 7 all squared, and we're saying that dy by dx, well, not we're saying, we've found that dy by dx is 2 times 6x times 3x squared plus 7. So the most important thing we notice is that the bracket is the same, and that's true for the other functions in our table. So what about the 2 and the 6x? Well, if we look at 3x squared plus 7 and differentiate that, it gives us 6x. So we can call that g of x, which links in with what we had before. So that's the inner function, or the first thing that's going to act on x. If we were finding out what the value of x was for this whole function, we'd first put it into that inside the bracket. And so that's our g of x. And if we're differentiating g of x to get g dashed of x, that's our 6x. Now, the bracket is whatever's inside the bracket squared. So that means our outer function, f of, I've put z so that z stands for something other than x. Obviously it's still true for x, but in this situation we don't have x in the bracket, we have g of x in the bracket. But certainly what's happening now, if we had just a variable z in the bracket, we've got z squared, and when we differentiate that we get 2z. And that's what's happened on the left there. We had a bracket squared, the squared has gone down to 1, which we don't write, of course, and we've multiplied by the power, which is the 2 at the beginning. So we have y equals 3x squared plus 7 squared. As I mentioned, the 3x squared plus 7 is our g of x, so that goes inside the bracket, and f, which is x squared, then acts on it. So when we differentiate, what have we got? Well, we have g dashed of x, which is the red circled 6x on the left, and we also have f dashed of g of x because we have 2 times the bracket to the power of 1, which is the f differentiated, but then in the bracket there we have our 3x squared plus 7, or our g of x. So let's go back to that nasty big function that we had and see if it works for that one. So we've used those simpler ones, simpler functions, to see if we can spot a pattern, and we spotted a pattern, and we think that we have the chain rule there. So let's apply what that rule is to this nasty one from before. So we know from before that when we multiply that cubic out, we get x to the power of 6 plus 6x to the 5, etc. and by differentiating bit by bit we get this 6x to the 5 plus 30x to the 4, etc. So we know that that's what we should get if we're going to use some other sort of way of finding out what the function differentiated is. So let's see whether our new chain rule works. Well, if that function is f of g of x, then our inner function, the g of x, is the x squared plus 2x minus 3, and the outer function is f of x equals x cubed. So when we differentiate them, f dashed of x, so x cubed differentiated is 3x squared, g dashed, well, x squared plus 2x minus 3 differentiated is just 2x plus 2. Okay, so we're claiming that dy by dx is this g dashed of x times f dashed of g of x. Does it work? Well, let's pop those in. So we have our g dash, which I just wrote before, and then we have 3 times x squared, but x in this case is the inside of the bracket, which is our g of x, of course. So we pop that in there. Now, we do have to do a bit of work to show that that is the same as the one we worked out before. So, first of all, the second bracket there, the x squared plus 2x minus 3 squared, is shown multiplied out, and the first line of that is the x squared plus 2x minus 3 being times by x squared. The next line is when you times it by 2x, and the next line is when you times it by minus 3. And of course you're going to take notes from this video so you can check all that out for yourself. And then on the final line you can see now we've multiplied the first bracket by the 3, giving us 6x plus 6, and we've gathered all the like terms together to give us the second bracket. And we've still then got to multiply those brackets out. So again, the first line there is 6x times the second bracket, and the next line is 6 times the second bracket. And you'll notice I've staggered them, so it makes collecting the terms together nice and easy, and we get 6x to the 5 plus 30x to the 4 plus 12x cubed, etc. And it does indeed equal what we got from multiplying it out and differentiating before. So this shows us that for this more complicated function our chain rule works. So we conclude that for the function y equals f of g of x, we have dy by dx is g dashed of x times f dashed of g of x. And that is called the chain rule, or the function of a function rule. We must bear in mind, however, that these demonstrations of functions that do work don't constitute a mathematical proof, so we haven't proven the chain rule, and we do have a proof of that in another video, but it is true. I'm telling you it's true, and you can now use it for relevant examples.